Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this quick video, we will look at LeNet 5 architecture and how the input and output shapes of these various layers are calculated by following this classic formula of calculating the output shape of a CNN layer given the input shape. So first, this is the architecture at the top image here. So I'm starting with a 32 by 32 by 1 grayscale image. Then it goes to a 5 by 5 kernel, the first convolution layer, and outputs a 28 by 28 by 6 image. That is 6 here is a channel, and my output, the output width and height both are 28. Then I apply an average pool of stride equal to 2 and filter of size 2, and I get an output of 14 by 14 by 6. On these I apply the second conv2, and the output of this conv2 is 10 by 10 by 16. 16 is a channel here. And finally the average pool with stride equal to 2, filter size 2, and I get my matrix, the output matrix of 5 by 5 by 16. And this kind of the last matrix, because after these I get a fully connected layer which is a vector. So after this layer I get a vector with 120 elements that will be again changed to 84, and finally my softmax layer, which will give me my final prediction, which is a 10 class representing the 10 labels of MNIST dataset. Yeah, so the entire thing is applied on the MNIST dataset, which has 10 classes and consists of only grayscale image. Now the in this video we'll understand these number, how they are getting converted from 32 by 32 to 28, then 14, then 10, and then finally 5, and then finally to a fully connected layer. So that's to understand that we have to apply this classic formula. It's a single, both I'm showing here two formulas. Actually it's the same formula, which is the top one for calculating the output shape of a convolution layer given the input shape. And it's super simple. You just do these addition and division. That is here n input is a number of input features, and in output is a number of output features. And when I say input features and output features, it could be either height or width. So if my n here is height, my output will be n height. That is I will get the output shape of the height dimension. So anyway, so n is the number of input features. 2p, p is the padding size minus k, k is the filter size or the kernel size, s is stride, and to this whole expression you just add 1. So this is the normal convolution layer calculation. And for a pooling layer, because we have two average pooling layer here, for the pooling layer the same formula becomes just simplified to this, because for the pooling layer there is no padding. That means I only deduct my input features minus filter size divided by stride, and to this whole expression add the 1. So here I have taken example w here represent w width. So this is my input width, and after applying this formula I get my output width. Now let's apply this formula to understand our first layer, which the input to the first convolution layer is 32 by 32, and I apply a 5 by 5 filter with a stride of 1, and I should get a 28 by 28. Let's do my calculation. I'm just copying and pasting the relevant numbers here in this cell. All right, so that's my calculation. Input image is 32 by 32 by 1. Convolution, in the convolution layer I have k equal to 6, s equal to 1, p equal to 0, padding is 0, kernel size is 5 by 5, and k6 that is a number of channels. So that's just by the architecture of LeNet 5, that in after the convolution the depth is increased, so I get a higher number of channels. And let's just input these numbers into this formula here, and I get so the formula is this: input width minus kernel width plus 2 into padding, divide this whole expression by stride, and then this whole expression also need to be added with a +1. And if you do this calculation, 32 minus 5 plus 2 into 0 divided by 1 plus 1 gives you 28. And the same way, if you do this calculation for the height, that is input height minus kernel height plus 2 into padding, divide the whole thing by stride, and then to this whole calculation add 1, and that would give you 32 minus 5 plus 2 into 0 divide by 1 plus 1 is 22. So that's how we get these the output from the first conv layer as 22 by 6, and that's exactly what we just calculated here. And now you will see the second calculation here. Our second one is an average pooling, and now as an input to this average pooling, I will have 28 by 28 images, and the output from the average pooling is 14 by 14. Let's see. So my calculation is this cell here. So here my padding is 0, stride is 2, filter size is 2 by 2, and if I just include these numbers into my formula, input width minus filter width by stride plus 1, I get 14. Same for height. Input height minus filter height by stride plus 1 gives me 14. And again, I got these numbers, 14 by 14 by 6. And 6, of course, is part of the architecture of LeNet 5. That's how my total number of channel, that is the depth of the network at this layer, is 6 I have kept. But we got the exact calculation of how 28 turned into 14 after the average pooling. All right, the next one is my second convolution, and here my input image out of size 14 by 14, that is coming from the previous pooling layer. So let's do the calculation here again. So I'm just pasting the calculation in this cell, and this is a calculation. So input width here is 14, and input height is also 14. Stride remains 1, padding is 0, and kernel size is 5 by 5. Just include this number, I get 10 as the output of this formula, and for output height as well I get 10, and that's exactly what we have here at the conv2 output. The conv2 output is 10 by 10 by 16, and 16 is again the number of channels, which is part of the architecture. And the next one is the second pooling layer, and by looking at the architecture, I can see here the input will be 10 by 10, filter size is 2 by 2, stride is 2. So let's put the calculation here. All right, input height is 10, input width and input height both are 10, and my filter width is 2 because filter size is 2 by 2. So just including the and padding is 0, stride is 2 again. So just input this number to my formula, and I get the output from this second pooling layer as 5 for width and 5 for height as well, and that's exactly matches with the architecture image here, 5 by 5 by 16 after applying the average pooling. And then the first fully connected layer, there I have I need to get practically 1 by 1 by 120, because here it's a fully connected layer, and which is a vector of size 120. So I should get a width of 1, height of 1, and only then this one matches. That is, this vector actually represent 1 multiplied by 1 multiplied by 120. So let's just do the calculation. And here's my calculation. Here my input width and height is 5, coming from the previous layer. Stride is 1, padding is 0, and kernel size is 5 by 5. So just include this number to get the output width. So 5 is input width minus filter width is 5, that is a kernel size, divide by 1 and multiply add the whole thing by 1, and you get 1. Exactly same calculation for height. 5 minus 5 by 1 whole plus 1 gives you 1. All right, so now and the output depth is 120. So the output vector matches exactly what I was saying. The output vector is output width multiplied by output height multiplied by output depth. That is 1 into 1 into 120, and that's exactly what we have in this fully connected layer. So that was so that's how the calculation is made. LeNet 5 is a classical and super simple neural network architecture, but this formula in this way you can apply to any neural network architecture that you are doing to make sense of these size numbers. And now I am going to implement the same architecture in PyTorch, and I will not go too much in detail into the every step because just few days back I made a separate video on LeNet 5 architecture from scratch. Here is that video. I will put a link in the description of this video. Here I went in detail of step by step every line pretty much that to implement this LeNet architecture from scratch with PyTorch. So what I'm going to do, I'm going to take the same code here that I built in that video and see that it's working, that and all this calculation that we just did here that actually matches with the output of PyTorch layers. So let's first import all the relevant libraries, which are these. Only the regular one, torch and torch.nn conv2d. Only extra thing is that I want to import this extra library called torch summary. This line from torch summary import summary, so that I can print all the layers in a beautiful way. So the code for the architecture is just this. Let me copy it from my other file. Yeah, here it is. So this is the code for implementing the same architecture. So overall we have two conv layer, two subsampling layer, which is my max pool 2D layer here. That is, I'm not using the average pool, I'm using max pool just because kind of max pool is currently the most popular one. Average pooling is slightly falling out of the popularity contest. And I also have three fully connected layer. The first one is here FC, the second one is FC1 and FC2. So just look at the original architecture here again. I'm starting with 32 by 32 by 1. First conv layer, which is outputting 28 by 28 by 6. Then an average pool. In this case, for my code, I'm using max pool. From there, I'm getting a 14 by 14 by 6. Then I am applying the second conv, then another average pool or max pool in my case, and then after this I'm getting my first fully connected, then another fully connected, and then finally the output from the neural network. And this is our code. So my self.layer1 is includes my conv2d and my max pool 2d, and of course I have included my batch norm and ReLU inside these layer 1. Then layer 2, I have conv2d, max pool 2d, and again batch norm or ReLU are included in this. And then after these layer 1, layer 2, I have my fully connected, then another ReLU, then next fully connected, then another ReLU, and finally these FC2, which is the last fully connected one. And then my forward function, this will just implement these same architecture layer by layer. That is, the output from the previous layer will be the input to my next layer. All right, now let's run this, and I am going to take a dummy tensor to check that this is working. Let's go my next cell. All right, so what I'm doing is I'm just creating another the object from this class and passing it the number of classes as 10, because this LeNet 5 was specifically designed for MNIST dataset, which is of 10 classes, and that's why I'm passing 10. And to the input size, I'm just passing 1 by 32 by 32, because that's how it expects the input to be. Remember the input image at the very first stage to the entire network, I have to pass a 32 by 32 by 1. 1 is a number of channel because it's grayscale. So this is what I'm doing in my summary function, and summary function is just what we discussed. that this is from this package torch summary. So input layer is a tensor, which is 1 by 32 by 32, and device I'm mentioning CPU, and that's just because that is kind of required for the summary package to run properly in the local machine. I could not run it with GPU. All right, that's a separate thing. So just mention your device to be CPU if you are running summary in local machine to get the correct output. All right, now just run this cell, and beautiful. I got the entire output very well presented here. So let's understand. So my first conv2d output is 28 by 28 by 6, exactly what matched with this one. Let's put this image into that cell down below so that we don't have to go back and forth again and again. Let's just put a markdown here, and yeah, perfect. Now what I'm seeing is, so this 28 by 28 matches with here after the first conv layer. Then I am getting another same dimension, that is 6 by 28 by 28. That because I have a batch norm 2D and ReLU before my first max pool 2D. So they are batch norm 2D and ReLU. They will not change the dimensions, and that's why I'm getting the same dimension here as well. Then my max pool 2D, and from there I'm getting 14 by 14, exactly what is required here and what we saw by our manual calculation. And then the next conv 2D, from there I'm getting 10 by 10. Here also in the image it's 10 by 10. And then batch norm 2D and ReLU again, which will not change the dimension because in the layer 2 as well, I have my batch norm and ReLU inside this layer 2. All right, and then after my second ReLU, okay, this is the second subsampling, that is the second max pool 2D. Here I should get 16 by 5 by 5, and that's exactly what the architecture as well, 5 by 5 by 16. And then after that is a fully connected layer. So fully connected layer, I'm getting -1 and 120. -1 just represent that this dimension is to be inferred, and here in the PyTorch case of PyTorch, for all these cases, the first dimension is the number of samples in a batch, that is a batch size. So anyway, linear one is 120, what we see in the image as well, it's 120, and that's what we also got by our calculation. Remember, when we calculated the first fully connected layer, we got 120. And after the first fully connected layer, I got after 120, then next is 84, and that's what we are getting here. And I have a ReLU after this, so that's why I am getting another 84 here. That will not change the dimension. And finally, from the output of the entire network, this is the 10 classes, and that's what I get here, that it's a vector of 10 elements representing 10 separate classes of MNIST dataset. And total number of parameters, trainable parameters, are 61750. And yeah, so we saw that the entire calculation of this LeNet 5, all these sizes calculated manually, exactly matched after we implemented this with PyTorch. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one.